and thank you, and for having me. I would like to make it as interactive as possible. So if you are able, turn on your cameras and speak, because it would be nice to have feedback rather than just me talking by myself. So yeah, please feel free to just like make it more lively. What I'm going to talk about is a little bit about what we do in the City Intelligence Lab. So first of all, I'm Angelos.
Maybe Angelos, I can give a brief background information of yours. Of course, we all know you, but maybe for those who wants to know you better, I can just say a couple of words.
Sure.
Angelos is the head of the City Intelligence Lab at the Austrian Institute of Technology in Vienna, and he teaches at the Institute for Advanced Architecture of Catalonia. He studied architecture at the University of Patras and computational design at the Bartlett, UCL, and he has been a Marie-Curie Fellow at the Innochain Innovative Training Network. He has previously worked as an associate at Foster+Partners and has taught at the Bartlett, UCL, the Bauhaus University, the IUAV in Venice, and the TU Graz. His research focuses on performance-driven design and simulation, but he has worked in various fields, including AI and machine learning, AR, VR, 3D scanning, digital fabrication, and interactive installations. He has led the development of various design systems and simulation interfaces, including infrared and AI-based design framework for urban planning. And then the floor is yours, Angelos, with the title of your seminar, Reinventing Performance-Driven Design Through AI, the Case of Infrared. Thank you.
Thank you very much. Thanks for the introduction. So yeah, I mean, let's just share my screen here. Yeah, as I said, please feel free to interrupt, make it more interactive, and sort of like drop in questions. So I'm just going to talk a little bit about what the City Intelligence Lab is, because perhaps you don't know it, and most probably you don't know the Austrian Institute of Technology. If you do, that's great. If you don't, we are not a university. We don't teach, like there's no like courses, but we also not a company. We're like this weird in between hybrid between academia and a company. So half of it is owned by the government, half of it is owned by the Austrian Federation of Industries. And essentially what AIT is it's a research and training organization, but what it is essentially an organization that tries to take academic research or like scientific research and bring it into an application for the industry, so that the industry can actually adopt it and use it. Of course, AIT is like much bigger than our unit, and our center has different centers, different units. We are in the Digital Resilient Cities unit, which is focusing on, of course, cities and urban planning and smart cities and energy. And we are in the Center for Energy. The AIT generally has like around 1,300, 1,400 employees, and we are a smaller unit of about 60 people or so. We do projects all around the world. We've done some in Turkey as well, as mentioned, and maybe what we do is, it can be summarized into urban transformation and resilience. Like, how do you really help cities transform into becoming more energy efficient, sustainable, livable cities and smarter cities? So there's a lot of smart city work that we do. There's a lot of like energy resource management, of course, urban resilience, climate resilience, but not only climate resilience, but generally urban resilience in the sense. Of course, climate adaptation is a huge part of it. And where we, the City Intelligence Lab, focus mostly is urban analysis and simulation, computational urban design. Of course, that's what we're here to discuss. And we do also a lot of like interactive interfaces and mixed reality, AR, VR. The City Intelligence Lab is essentially a sort of like lab within the uni that is sort of like considered an incubator for new technology. So what we're trying to do is bring new technology solutions to the overall unit and to the sort of like to an intelligent, let's say, urban design workflow. This is what it looks like. You have like these projectors and these AR models, etc. We pretend that we're working there. So what we really are trying to do, as I was saying again, is like to bring all of the different aspects of performance, of the different aspects of sort of like climate or energy or economical performance into the urban planning workflows. So to call it in one term, integrated urban planning, integrated performance-driven urban planning. We are the City Intelligence Lab and my team. We are very much associated to the CODEC project, which was initiated by Professor Reinhard Koenig, who is still heading the project with me. I'm sorry. Cognitive urban design computation is the title of CODEC, and essentially what it's trying to do again is there's been 5 PhD students, there's been like different master students, and like it's a program that's been running for 5 years, and what its research aim is to understand the cognitive aspect of urban design computation. So essentially, how do we interact, use and integrate these computational urban design models in order to make our urban design workflows more intelligent and more efficient. I'm sorry about the voice. So since we're here to talk about performance-driven design, I'm gonna just do like a little bit like of a history sort of like exercise. Does anybody know this thingy? This is where I'd like some interaction if possible. Not really, right?
No, this brings back memories.
Yeah, I'm sure you do.
I was just going to say, from excitement, I couldn't unmute myself. Thank you.
Yeah, so this is generative components. It's really old. So it's at least maybe 15 years old now. And this was sort of like
kindly.
This was sort of like the beginning of computation, or of like parametric design with Bentley's microstation using generative components to essentially produce complex forms. If we look at what we have today, we've gone a little bit far. We have like spaghettis of very complex sort of like grasshopper definitions, Python scripts, and what have you. So we've gone a little bit far with computational design. And if we look at performance-driven design, I think very few people would know this one. Back in the day when we had GC, people were trying to connect GC with some sort of like environmental analysis module, and in this case it was Ecotect back then, and this was a connection between generative components and Ecotect, which could actually give you a solar radiation calculation on a free-form surface. This was very difficult to achieve, and you had to like download some custom DLLs and put them in special folders and really weird things you had to do to make it work. I actually never managed. I was struggling with this thing for a while, and for a few weeks I never managed to make it work. Today you go to Food for Rhyme and you download like 20 plugins, and you have like suddenly your FEM, your CFD, your dynamic relaxation, your kangaroo, your caramba, your whatever, and then you can very quickly analyze very efficiently analyze your design. Integration of performance simulation has gone a lot far, but we think it can go a lot further, and this is what I want to talk about today. What we've done in this overall scheme is not me, but the work that has been done in the lab before me is Decoding Spaces. You probably know Decoding Spaces if you've worked a little bit in the urban scale. It's a toolbox that sort of like has a generative and analytical aspect to urban master planning scenarios, also including all of the space syntax metrics. It's a collaboration between AIT, Bauhaus, ETH, and Future Cities Laboratory. So it does things like allows you to generate street networks, or allows you to generate quickly like different typologies and experiment with typologies. I hope the videos are running. Okay, yeah. Can I get an okay, Özlem? Yep. Can you see the videos?
Yes.
Super. Okay.
Yep.
So yeah, like it allows you to do like, quick sort of like typology experimentations, or to actually design whole master plans very, very quickly, generatively, and just like input a few numbers and essentially get solutions to test very, very quickly. We also do a lot of analytical work. So in this case, all of the work you see is work we've done in the lab, sort of like custom scripts that we've created in Grasshopper or Python or whatever. In this case, you see you can put a position in a city, in a network of transportation, and you can see what you can reach in a city very, very quickly with different modes of transportation: walking, bicycle, cycling, trains, trams, etc. And that helps you really understand sort of like what the accessibility of things in a city, and also to plan or analyze or plan transportation lines. For example, you can plan a new tram station or train station, and very quickly analyze how it affects the existing network. We also do a lot of climate simulations, and we've built our own climate simulation. In this case, we built a flooding rainfall of simulation, where you can have a particle system which shows you where rain goes through in a city, and in that way you can identify problematic areas. You can figure out what buildings could be affected, and then sort of like come up with resilience metrics. But if we go back to this idea, I'm not going to talk too much about like all of the work that we do. I just want to focus on one specific topic. If we go back to this idea of like the sort of like the gap between design and performance, the problem that we had 15 years ago is still here, which is all of these simulations, these analyses, they take a lot of time. They are very difficult to integrate. Even if they're integrated in the ecosystem of our design systems, then they're still very slow or very difficult to perform. For example, a simulation like this, the rainfall could take a whole day to perform. If you mention like a simulation of wind, for example, it takes an even longer time. So that's what infrared is about. So infrared it stands for Intelligent Framework for Resilient Design. Is, as I said, it's an AI-driven simulation framework which allows us to perform simulations much faster and much more efficient. So the example of the wind simulation is a great one. If you wanted to do a wind simulation in an urban scenario, you probably need at least 2 days to prepare it and a day to run it, or something like that, if you're not an absolute expert on it. The same exact simulation result, infrared can predict in a second. And this is what I wanted to show today, which is kind of like a breakthrough for us. 1 second. So how do we do that? Would be, of course, the logical question. We use machine learning, we use deep learning networks, like GANs and other networks, or models that allow us to sort of like learn a relationship between input and output. Perhaps you've seen things like that, GAN networks and the internet, or like, taking a sketch and make it into render, or taking a photograph and making it into a Monet or Van Gogh or a Cézanne painting or something like that. Or taking yourself and make you look like your dad. This is all the same sort of like technology, the same sort of like models. What does that have to do with us? Of course, is interesting. This is probably the best sort of like image of how to explain the project. On one side you have a simulation, and on the other side you have a prediction of that simulation. One takes half an hour to run, the other is running in a second or so, in real time actually. So this is sort of like the breakthrough. And how do we do that? We take cities all around the world, like Vienna, for example. In this case, you take parcels of the city, you create 3D models of the city, and then you run all of these analyses, right? You really have to run tons of simulations to be able to create these models. Once you've done that, you can then train a machine learning model, a neural network model, to predict the result. In this case, you have like an input and you have the simulation and the prediction, and you can see that it goes quite well. So Infrared already works in different sort of like in different performance models like heat, wind, and solar radiation. We are like also expanding to noise, rain, and traffic. And what I wanted to, and yeah, of course, we can combine infrared with other AI or non-AI driven methods of analytics, like for example, the space syntax analytics. They're not that complicated to run, so you can run quite faster. So what we've done with infrared is essentially combine different performance feedback methods, which all are near real time, into a bigger sort of like framework that allows designers to really get instant answers and sort of like intuitive answers on their design decisions. So what I wanted to show you is how infrared is used in a project, for example, using all of these different analysis models, both the AI and non-AI, in a project that we've done. So in this case, this is a project in Norway, which we try to do. It's a master plan on a waterfront, and you can see like the different aspects of all of these things that I talked about. So there's the massing aspect. Of course, you can very quickly change street layouts, and as I said, with using decoding spaces, and you can just very quickly, manually or non-manually or generatively, you can change certain parameters and generate different massing options, right? That's the easy part, I suppose. Then, of course, you have all the microclimate studies, which are done with infrared, which allow you to have real-time answers on wind, solar radiation, sunlight hours, etc. And also not just static answers, but you can actually look at the conditions of wind, for example, throughout the whole year, or throughout different times of the day, or all the different sort of like wind speeds that you get in that area, which is a very important part because it's a waterfront development. Or you can do more intuitive things, like for example, in this case, you have a park and you position the park inside this quarter, and you can move it around, and you can in real time see how it affects the wind comfort. This is something that was we don't know if exists anywhere else, so that's sort of like a little bit proud of it. And again, you combine that with changing the street layouts or changing the massing options, and then in this case you just take off a street part, and then you automatically generate a new building, and you automatically generate also the map, the wind map, and understand what it does. So that's a different way of designing. It allows you to sort of like very quickly and intuitively test solutions. You can of course do more manual things like knock off 2 buildings and add a tower or something like that, while at the same time what TFA you have and you are trying to achieve, and how would that affect essentially the wind condition is also what you get immediately. In this case, you move the tower around and you see where is the best location to put it. Again, all of that would not of course be impossible if you needed 2 days per simulation run. Yeah, we of course have all the other sort of like analysis, sunlight hours and solar radiation. Wind is probably the most complex. That's why we're focusing on that. And at the same time that you can look at all these microclimate studies, you can also understand the accessibility of this design. So looking at things like centrality measures or density measures, or actually understanding your access to parks or to retail units, again, through different transport modes. And you can combine, in this case, the climate with the accessibility. So essentially you both know where a park is, but also how much it's hit by wind, for example, which is something that's very, very interesting to have. You can, of course, move the park around as you do for the wind, and understand at the same time how many units have access to that park. So even if you put it in the best location, for example, in terms of wind, it doesn't mean that you have the best location in terms of accessibility. So you need to sort of like start juggling the different metrics. And of course, as we said, there's transportation analysis, where you can put a sort of like a series of train stops or tram stops in your design, and understand what sort of like percentage of your population is accessing these different train stops, and then you can also move them around and fine tune where they are in relation to bridges perhaps you have built, or where they can be located. Of course, you still combine that with microclimate, and that sort of like gives you a very, very big and holistic picture. And finally, like noise, what population of your quarter is hit by noise. So all of these different performance aspects you can really sort of like assess in a very, very fast and intuitive manner. And this is what infrared is about. And we've developed sort of like infrared in a way that it's not just, you don't really need to come to us to use it. You can also, like, it's also used through other methods. In this case, so I'm going to start the video. In this case, we've integrated in Giraffe. We've integrated infrared in Giraffe, where we have allowed Giraffe to like query our wind comfort studies. And I don't know if you know Giraffe. It's an online platform for urban planning. Essentially, what we do is we have an API where Giraffe is contacting us and getting a result directly from infrared, and it's integrated in their own sort of like design system. And in this case, you can do the same thing, like move the buildings around, change the building's configuration, and get instant answers of the wind. I'd like to attempt this very quickly, if possible, and give you a live demo of what infrared looks like. Hopefully it's not into some sort of like maintenance mode or something. I haven't notified the team that I'm doing this. So I'm just going to create a new project just to show you a little bit how it works. Maybe I go to Istanbul. I don't know if you're like OpenStreetMaps are very sort of like much informed, but we'll see. My connection will probably delay this a little bit. So here we are in Istanbul, but I don't think you have any sort of like 3D data. I'm just going to choose a random location to not mind my sort of like ignorance of the environment. Sorry, 1 second. So I'm going to say here. I was going to do like that. And oops, 1 second. My connection is a little bit slow because I'm presenting at the same time. Okay. Yeah, okay. 1 second. I might have to like turn off the screen and start again because. Okay, I think that. Come on. Let me stop sharing for a minute because I think that's the problem.
Sure.
1 second. It might be slow for like, because it's all based on sort of like online resources. So I'm going to share my screen again. So can you see the screen yet?
Not yet.
Interesting.
Maybe you can share again.
Now?
Yeah.
So it
you see the
some
model.
data. Yeah, super. So it retrieves some data. Of course, in this case, you don't have like height in the OpenStreetMaps sort of like buildings, but it's okay. We can assume that this is sort of like the average height of the buildings. And here you can add like things like, for example, wind comfort and wind direction, and then you can add the different analysis you want to run. I'm just going to do very quick sort of like demo to show you how actually fast this is. Solar radiation, sunlight hours are only for Vienna, but we can assume that they're the same. So I'm just going to delete these buildings here, and I hope I'm not insulting anyone's and demolishing anyone's building, but I'm just gonna. I don't even know where this is. So I'm just going to build the tower here. So I'm just going to start designing something and say, okay, what happens if I add, let's say, a new sort of like high-rise development here, right? I was going to do a very quick design, it doesn't really matter. And this is essentially what I want to show you is like how quickly you can go from like start designing something to getting a sort of like performance feedback from it. Hopefully this will get back in a few seconds, and you will be able to see it. So any questions up to now while it's loading? No.
No,
Yeah.
I guess.
Is it open source? I mean, can we add some more data? Like, let's say we're working on this area is in Istanbul and we model it. Can we also upload our model to your system? Or
Open source, no, it's not open. I mean, some of the things that we do are open source, but in this case, it's also not free. We actually license it at this moment. But if you are interested, please contact me afterwards, and we can see how we can make it work, right?
Okay.
So this is like wind comfort studies, for example. This is wind speed studies. This is solar radiation and sunlight. I was like, you all get all these sort of like different analysis very, very quickly. So I'm gonna go back to the presentation. So that's like how this is our like web app. This is how quickly you can do things on the web. But of course, we do the same thing in Grasshopper and integrated in our own sort of like design systems. And what this allows us in the end to do is, apart from like just iteratively sort of like test solutions, we can also do a generative design exercises. Like in this case, what we were presenting in CIMAD a couple of years ago was how you can combine all of these sort of like real-time fast simulation methods to go from this iterative sort of like testing of and modeling to creating a whole solution space and then sort of like analyzing the solution space and trying to derive best solutions. But our focus here is to not stay in the sort of like black boxes of optimization with genetic algorithms or what have you, but to actually combine the two worlds. And in this case, you bring back the model. We have a bit of an AR component here. You bring back the model and you can continue to manually play around with it. In this case, you add a couple of towers, or you sort of like change some sort of like some orientation of the buildings, etc. And what we've also done in this case is we've taken a step further, where we have this real-time simulations, but we also have this sort of like cognitive problem of where do you put this tower exactly so that it's the best sort of like solution. And then you use something like reinforcement learning to find sort of like the optimal position of that tower. So combining different AI methods to do that. And finally, yeah, this is how it all looks when we're doing it in the lab. So this is sort of like a video, a bit of a cheesy video, where we have like these different interfaces and we're bringing the design in the table. The AR part is actually important in understanding and negotiating these solutions on the sort of like actual model and the physical model, and sort of like selecting the different parameters and looking at the result in real space and real time. So in this case, this is the combination of all the things, the real-time analysis with the sort of like intuitiveness of the AR models. And maybe it's more interesting to see that in a project like Treehopper, for example, which we did a couple of months, 3 months ago in the city of Vienna. We won this hackathon of solutions, climate solutions, and Treehopper is addressing essentially it's a tool that's addressing the problem of planting 25,000 trees in the city of Vienna, which is what the government aims to do. I'm just going to turn off the music. So essentially, you get this sort of like crowdsourced, like sort of like a participatory process of planting the trees, and you need to figure out where the people want the trees, but where it's also feasible to put the trees. So you have this average Joe person goes online and finds Treehopper, and then you can actually put the trees in any location you want, and it gives you in real time both the sort of like analysis of the microclimate, what does it do, how much shading does it provide, how much wind protection does it provide, etc., how feasible it is to put the tree there, of course taking into account the substrate of the streets, but also allows you to see the tree there and actually see how it looks like in that location through the augmented reality app. This is a mock-up, but like with actual components that work. Like all of this is it's not spoofed, it's actually working. And you can actually like walk around and see the trees there and see like what it looks like. And the idea here is like you can actually start negotiating with others, with city planners, with other citizens, and with other sort of like interested parties on where the best locations are. And you have like actual debates about where the trees can be put, and look at the different solutions, and then again use AR to sort of like look at the solutions in a more like planning perspective, which is what they're doing here. This is the team, by the way, which is the team that's behind all of this, the team that sort of like does all of these work, and I'm extremely proud of them. And yeah, finally, this is our website. I'm just going to share it with you, and I think that this is going to be the end of it. Any questions? I would be very happy to answer.
Angelos, hi again.
Hi.
Thank you so much.
Thank you.
The first question is about the image translation deep learning part. You generally work on the flat surfaces, I understand.
Yeah.
For the
we're working on the ground level.
Yeah, ground level. Do you have any plan about the 3D slope areas? Do you have any?
We don't work on the ground level, as in the analysis is not on the ground level. The analysis is a 3D analysis. It's a proper 3D.
Yeah.
But we are looking at the result at the ground level. We have also done work with facades. We've also done work with interiors, but yeah, this is not what we've looked at here.
My question is more about the image translation is working for 2D plans. I mean, you get input data for 2D outputs. So you gave those 2D outputs as input for your deep learning model.
Yeah.
Do you have any solution or brainstorming for 3D things, or you just inform the model as contextual things?
So
like
the image-to-image translation is only one of the AI components we are dealing with. There's a lot of like, we do a lot of like AI work on 3D representations as well, but also on sort of like I mean, it doesn't really matter if it's 2D or 3D, it's vectors in the end. But if I'm trying to understand what you're asking, is essentially how do you use for example GANs or other image-to-image translation models in a 3D environment? And I think that the answer to that is always it relates to your domain, the problem that you're trying to set out. So if you're trying to figure out a facade, for example, problem, then you need to build a model for facades. If you're trying to and there's different ways of doing that. Like there's different ways of representing information to color or 2D or 3D images or 3D vectors or what have you. It doesn't, in this case, we're not really looking at images, to be honest. We don't do image-to-image translation in this case. We do it's vectors, so it's not exactly images, but anyway, there's different ways of representing information. You can represent information, 3D information, in a 2D way as well. So it depends what your problem is. I would say that's my answer.
Okay, thank you.
Any other question?
Hello.
Hi.
Angelos. Thank you again.
Pleasure.
I'm also an instructor in ITU, and I'm very happy to hear you because one of my PhD students is also start working in city intelligence. He's also here too. Yeah, Nihat, are you here? maybe, yeah, you agree.
I'm here.
Okay.
Hi.
Okay, I would like to, yeah, I hope we keep in touch. I would like to just really work, and try to, understand your infrareds. So if you can give us some access, maybe for some time, so we can understand it. Also, like we are also interested in, working in some historical district of Istanbul. So there are layers, many layers from Byzantium, Ottoman, and now, and how do you think we can, work in an AI way with these layers? I would like to get some information from past and maybe use it for the future. So, do you have any experience about it?
Definitely. Like we recently had a visiting researcher, Iason Zero. He's working in Cyprus, and he's working in exactly that, like historic.
What do you think? What do you say his name is? Yes.
Iason Zero. I can connect you if you send me an email afterwards.
Okay. Yeah.
I can connect you to him directly, because I think that your work would be very, very relevant. And I'm just gonna put like both things here. I'm gonna put my email. It's in the chat. So what we were doing with Iason is essentially trying to use these different layers, and that's why I was only talking about infrared here, but like there's a lot of other things that we do. So and sort of like essentially use sort of like data analytics, or like AI methods like clustering or other things to understand the interrelationship between like the historic layers of the neighborhood and things like microclimate. So for example, let's break it down to like actual meaningful things. Heat stress and archaeological sites, or heat stress and sort of like areas of interest from sort of like a cultural perspective, right? Or flooding and sort of like accessibility to different locations. So combining local residents movement, sort of like let's say walkability and accessibility to climate indicators and touristic or other sort of like activities. How do they play along each other? So if you have like these different layers digitized and sort of like well sort of like mapped, then you can start playing around with scenarios, with different solutions. So what happens if, for example, this pedestrian street is this sort of like car street is becoming pedestrianized? What happens if this other sort of like street becomes a park because it needs sort of like flooding solutions? What does it do to the accessibility? So like when you're combining all of these layers, again, you can extrapolate it into sort of like historic neighborhoods, which are like, it's not like you're building a new building and you need to put like, a tower here or there. It's essentially looking at the existing solution, but still the tactical interventions that you do in the city can affect a lot how the historical environment will be performing in the future in relation to climate, of course, and other topics. I mean, I hope somehow I answered the question.
Yeah. Thank you. I will look into it.
I'll connect you to Iason because I think that would be very interesting for you.
Yeah. We will send you an email.
Thank you. Anyone else? Senna, I'm not sure if you want to talk or you just turn on the camera. No. Okay. I'm trying to lure people into asking a question.
Angelos, hi again.
Yes, hi.
We gave a break in the jury, so I
That's
can ask
good.
you my questions. Sort of, what are the observations you have or your reflections on developing these models for different geographical locations or different cities?
Yeah.
I know that your group works on a bunch of different cities all around the world. So what's the difference? Do you have to tune the parameters
Models,
again and again?
Yeah. No, like this is a great question. So some of the models are global. Like for example, the wind simulation. That's a great thing about it. It's a global model, so it doesn't matter where you are. Of course, in every city you have to input different parameters to understand the different wind conditions, but it's the model is global. Some other models like solar radiation, you really need to build a lot of models, and you need to build a model for every city. That's inevitable because every city has different climate. And I think that we will eventually end up with models per different city. I think what's more interesting, what's more difficult is not just from the technical point of view, like, how do you build different models? This is very, very, very possible to do. You can build different models for every city. The issue is how do people understand and use these models? And people don't really need, and this is, I think, one of the mistakes we've done as professionals in integration of simulation, etc., is people don't need to really know what are the specifics of the climate models of every city, or what are the specifics. So like when an architect designs, he really doesn't need to and doesn't have to like learn every bit of environmental design. He really needs a sort of like tool that allows him to really get a rule of thumb solution, so it goes into a better direction. And this is the problem that we've always had is like, as experts, I think we want to keep more of the knowledge, and we say, no, you have to really do a very complex model. And it's not true, actually. You can actually create intuitive models and allow people to make decisions, because at the end of the day, this is what's going to save us, because we still are we should be generally ashamed as architects. We are the biggest contributors of greenhouse emissions in the world. So like we are the problem. Like it's not like automotive industries, it's us. So we are building buildings that are completely inefficient, and we need to change that. So that's that's my approach.
Great. So it is something you've been thinking about. That's interesting. And I'd be curious to follow up on what your approaches are to sort of open up different.
We need to build models. I think that we need to do that.
Yeah, but also maybe because it was interesting that you said this user end actually matters. So to build better models, or models that are better in the sense that you just mentioned, maybe we also need more input from the society as well, right?
Definitely, for sure. Like, and how people use, how architects use these models. So I'm also teaching environmental design in IAC. So it's very interesting. We actually taught infrared, both in IAC and in Berkeley and in some other sort of like schools. And it's interesting to see how it affects people's sort of like decision making. When you teach them, for example, Eddy 3D or open or Butterfly, so like the sort of like the standard in Grasshopper, which we call it the standard, but like for 99% of the architects is rocket science. So you teach them Eddy 3D, they get frustrated for a week. They're like, what is this crap? I can't use it. I was trying to do my simulation for like 12 hours and then it crashed or whatever. And then you give them infrared and then they just move a thing, and you're like, it changes how they work, right? But it also changes the perspective, and then it can be also dangerous, because they might think that they're like all on top of this, although you need to give them information that is actually useful and impactful on the design.
Thank you.
Pleasure. Other questions? I'm always available through email if you need.
I have a question, if you don't mind.
Sure.
I think what Mine, professor, asked was quite valuable, because we have all these tools mostly aimed for the development of AEC from the perspective of designers or maybe stakeholders or engineers at some point. But the part of the society where the other stakeholders, where the market who we serve, actually doesn't know how they can contribute by changing some of the parameters in the design process or something like that. So do you think your project, the infra, do you think it would be available for a common public use to understand what the dynamics are when they change their built environment just a tiny bit, or how they can contribute at one sense by seeing the impacts of their behavior change?
Totally. I think I understand a little bit better the question, the way you phrase it. You've got in this problem, like you have sort of like high-end architecture firms and academics, right? Like that they can do grasshoppers or sort of like advanced simulation methods, and we're like, especially academics are like, they want to perfect their models and make sure that they're absolutely sort of like accurate and all of that, which is for me nonsense. It doesn't really help the problem. Then you've got the developer, right? The developer is like, okay, yeah, whatever, like I need to build 700,000 square meters and they have to be, making me that much money, right? You want to make it environmental, that's fine. Like, and I can sort of like put it in my leaflet, and that's very environmental, but it still has to be 700,000 sort of like square meters. And then you have the user, like the person who dreams a house, and like they want to have the big windows, and they don't really care, like, unless it impacts them. I think, and that's a personal opinion, that once you've infused the climate resilience and sort of like, once you've infused the energy efficiency and all of those like components into all of these aspects, and that's why I think that really the very accurate models do not matter at this stage. Once you've given people the ability, the same way you've done already with energy ratings, right? You say your building is an A+ or whatever. That means that you're not gonna pay that much money when you're like turning your heating on. That means you're not gonna pay that much money when you're getting a certificate. Like, that's why the energy certificates are there, so that they make it, so that they infused in sort of like the whole process. I think this is what is the only solution. And of course, infrared is aimed at also the end user, where they can design their house, the dream house or whatever, and see how much they are affecting their own house or their environment by doing design decisions, by choosing like sort of like to put windows here or there, or to be that tall, that high, or like that short in terms of the building. So yes, I think that in order to do that, you really need to integrate the performance feedback in every aspect. The developer understands cost. They have to understand cost. So therefore, you need to give them also the cost impact of whatever you're doing. I think that's sort of like, unless we hopefully we see a political change in the way which this is all done. Until that, we need to figure out how do we actually affect the whole process. Yeah, for sure, like it's for the end user as well.
Yes, and to like add upon that, maybe at some point with your model is right now aiming for the new buildings, right?
Not necessarily. It's for all buildings as well. It's for.
So it's also for retrofitting and developing new interventions for the built environment.
Yeah, for
that's
sure.
Good.
Yeah, because like that's going to be the number one issue for
exactly.
existing areas. Yeah, and I'm pretty sure in Istanbul, I've worked on a few projects when I was at Foster's there. You have that really big issue, right? Like, master planning can be a lot like Greece. Okay, I'm going to demolish this area and I'm going to put like my new nice villas there, and like doesn't really work like that. Yeah.
Unfortunately. But thanks for the presentation and the answers. Yeah.
Cheers. Mm-hmm. So, well, I think thank you very much for having me. Unless there's another question, looking forward to seeing you all again.
In person, right?
In person, hopefully, yeah. Now that I got COVID, that I'm slowly getting COVID out of my body. Yeah, hopefully
Oh.
I'll meet people.
Get
Get
well
well
then.
soon.
Yeah.
Thank you. Thank you. Thank you for having me.
Yeah, Angelos, we would like to see you here in ITU.
Well, I'd be very
Okay.
happy to come now that I'm recovering.
No,
Feel free to
yeah.
Let me know if
Next
it's
time.
possible to organize it. Sure.
Yeah.
See you soon. Anyone?
Thank you.
My email is there. So thanks for having me. Cheers.
Thank you. See you.
Bye bye.
Thank you.